Now we have a gun that with an through an 80 centimeter barrel expels 40 gram bullet at 600 meters per second. Okay, well, here's the gun, and so here's the gun. I'm going to erase that because it makes it look like this applies to the gun, but it doesn't. This is going to apply to the bullet. Now, what we know is we're given the mass of the bullet, 40 grams. Delta V, well, it expels at 600 meters per second. Clearly, it starts from rest relative to the gun. And the delta T, which I gave as 0.1 second. Now, people started finding the acceleration, okay? And that's really a bad idea here because people wanted to find the acceleration using uniform acceleration. Well, the time to expel the bullet was given to be 100th of a second. I will tell you, and you may figure it out, that if that bullet accelerates uniformly through the 80 centimeters from rest up to 600 meters per second, it takes closer to 300ths of a second. So the acceleration is not stated to be uniform, and you really don't want to assume it. This problem said, I think this problem said, go ahead and assume it. But then there was an extraneous problem, which I asked people to do, that question, in the real world, since the acceleration is not constant, what are the implications? Same situation here, except we didn't specify uniformative acceleration, and there is no reason, therefore, to assume it. Okay, but we can use impulse momentum to find the average force. And other quantities. So what were we asked to find? Well, let's just go ahead and apply the impulse momentum theorem. And we calculate then that our average net force, and this is an average net force, and I've been all through here. You can look, putting a little bar over the F net. Now I didn't put a bar over that one, overlooked that one. This one does have a bar, but I'm going to make it a little darker. Okay. Net force is clearly then 2,400 newtons. We just plug in the 0.04 kilogram mass, the 600 meter per second change in velocity, and the 0.01 second time interval. Our change in momentum will be 24 kilogram meters per second, and divide that by the 100th of a second, we get 2,400 newtons. Now, what happens to the gun? Well, if the net force on the gun is just the reaction force, then it's going to be equal and opposite to this force. So we could use this force and calculate what would happen to the gun, but this would be an average force, so we don't bother. We just go directly to impulse momentum, and we know that the impulse of this force was 24 kilogram meters per second, the m delta v in this case. In this case, it's going to be equal and opposite. The impulse will be negative 24 kilogram meters per second. And that's going to equal the mass of the gun times the change in the gun's velocity. Well, the question was, what will the gun's velocity be? It starts from rest, it has this impulse, and it attains what velocity? Well, just solve this for delta V of the gun. You're given the mass, 4 kilograms, you divide that into the 24 kilogram meters per second, and you get what? Negative 4 meters per second. And that will be the change in velocity of the gun. If it started at rest, it ends up moving at negative 4 meters per second, while the bullet goes that way at 600 meters per second. And the bullet goes, the speed of the bullet will be 150 times the speed of the gun. And you can think about why, but that's because the mass of the gun is 150 times the mass of the bullet. And is that really true? The bullet's 40 grams. The gun is gun is 4 kilograms. I'm sorry. Yeah, the gun's 4 kilograms, its velocity would be 6 meters per second, so that the velocity of the bullet is 100 times that of the gun, because the mass of the gun is 100 times that of the bullet. Okay? And I'm still not sure. Mass of the gun is 4 kilograms. 6. Well, you can figure that out. The ratio of the masses and the ratio of the velocities will be inverse. Somehow my numbers are getting jumbled up.